panel. It's a 1-hour panel. It's going to be terrific. We've got Ben Sigrin first from National Renewable Energy Lab talking about forecasting loads with distributed resources. Then we have Patrick Dalton back to talk about both hosting capacity and interconnection. And then we'll wrap with Debbie Liu, who'll talk about locational net benefits, non-wires analysis, and sourcing distributed resources through programs, procurements, and pricing. So first up to bat is Ben, and following the presentation, I'll moderate Q&A. Please send your questions in at any time. And at the end of this presentation, we'll have a 15-minute break. So welcome, Ben.
Thank you, Elisa. Just confirm you can hear me. Okay, great. Thank you, everyone, for taking the time out of your day. So my name is Ben Sigrin. I'm a research engineer at NREL. I'd like to also thank Patrick and Debbie for joining the panel. My research at NREL focuses on forecasting customer-driven adoption of DERs, looking at how we can better model that, how we can better model consumer decision-making and the behavioral drivers of decision-making. So that culminates in the tool that we've developed at NREL called the DGen model, which I'll talk about later, and I'm happy to make a big announcement about today. Next slide, please. One more. I should also say portions of this presentation were developed by Andrew Mills at Lawrence Berkeley National Lab. So when we think about why DERs matter in load forecasts, there are several aspects here that are important. So first, as we're developing load forecasts, we're thinking about how we can make investments in the distribution system, better replace aging infrastructure, and planning for what the needs of the future will be. These DERs can help as part of procuring capacity and energy to meet peak demand and meet energy served. They can also be used as proactive investments to increase hosting capacity of the grid, which Patrick will talk about later. And then, of course, DERs can also be weighed against other policy objectives, other perhaps decarbonization goals, and so on. So it's all part of the mixture of trying to understand what are the costs and benefits of having customer-driven DER technologies. Next slide, please.
Hey, Ben, this is Lisa. We have a poll to queue up, I believe.
Okay. All right. So this is a poll, so please let us know what you think is the right answer here.
Ben, you want to provide the right answer?
Oh, yes, sorry. My bad. Okay, so thank you, everyone. So the, sorry, I'm trying to find my notes. I don't recall. Okay, so the correct answer is actually B. The correct answer is that there, through 2019, approximately 15.8 gigawatts of DC rated had been adopted in the United States through 2019. So people were close. Okay. So this is a schematic here. You may have seen similar concepts earlier in the training that trying to understand the impact of distributed solar that can have on transition distribution infrastructure investments. So the magenta line is what the peak load on the distribution system feeder would have been. Sorry, the blue line without PV generation, and then what is the net load with PV generation. And so that can either defer when the feeder's peak capacity has been reached, or of course there are other circumstances where, for example, the deferment is never reached if there's continuing energy efficiency investments or other changes to load patterns. Next slide. So this was another study that Lawrence Berkeley and NREL did, trying to quantify the impact or the value of increased accuracy in long-term forecasting. So this was run via a combination of capacity expansion and production cost modeling to see what would be the cost of either systematically over or under forecasting customer-driven distributed solar adoption. And so, of course, if you over forecast distributed solar adoption, then that means that less has actually been adopted than you planned for, and you will need to procure generation and capacity in some other way, which can be difficult to do and expensive. And if you under forecast DPV adoption, then of course it's the inverse, that more has been deployed and you've sort of overbuilt the grid, and that's an unnecessary expense to the ratepayer if that comes to pass. So the costs of misforecasting distributed DER adoption can be quite high. They can range in the order of millions of dollars per terawatt hours of sales. And of course, that's ultimately dependent on the level of penetration and the time period considered. Next slide. So another challenge in forecasting loads with DERs is trying to get at the differences between net load versus what some people call raw load. So raw load would be, actual load would be the amount of load on the grid that's actually consumed prior to the distributed solar generation or other DER generation. But what we actually usually observe at the nodal level is net load net of the DPV generation. So when we're developing load forecasts, we should be aware of that. There are regions of the country, cities, states, ISOs that have enough distributed solar adopted where it's a non-negligible correction to make. And so that's a methodological challenge, but there's a case study here about how PJM adjusted their net load and raw load forecasts. Historical assessments to develop a better load forecast. Next slide, please. So I think that many people in IRPs and DRPs are forecasting distributed solar, customer-driven distributed solar adoption. Of course, there are many other DERs that are starting to be adopted widely: electric vehicles, energy efficiency measures, price-responsive appliances, etc. So I think that we have to think about these other technologies as well in developing long-term planning studies. Also thinking about not all DERs are behind the meter; some can be in front of the meter, and so we outline a method that one can use to forecast distributed solar adoption, and I would posit that it can also be used to forecast adoption of these other technologies. In some cases, there are other types of DER systems. Combined heat and power is one that comes to mind, that are very specific to an end user, that are known to be of a large size. And in these cases, it might be the case that more of a local knowledge approach that the specific distribution planner might be aware of large investments that are coming online versus sort of the invisible customer-driven adoption. Next slide. So I'm happy to announce that this week, NREL open sourced its primary tool, which is called the DGen model, that is used to forecast and develop scenarios of future customer adoption of DER technologies. So if you have a GitHub account, please feel free to navigate to our site and browse the code and start using it. So this is part of a larger process for NREL, where we are participating with all 7 ISO RTOs to use this tool to develop joint forecasts, but also to build sort of staff capacity at the ISO level and their member level to use these tools and to improve the planning process. So for more information, please check out our website. And I would say that for anyone on the call that is trying to develop DER adoption forecasts, we're looking for additional partners for this study. We are funded at the moment, so we'd be happy to work with you to help you out to get started using the tool, or to point you to resources that already exist. Next slide, please. So this is an example of the forecast that we developed jointly with MISO staff. Please note that this is a pending publication. It is not considered a final result. But so essentially, we used the DGen model, and working with MISO staff, adjusted the inputs, adjusted the different parameters to better align with the long-term planning assumptions that MISO uses as compared to other ISOs or NREL generically. And we're also working on not just transferring the model code, but also transferring the data and thinking about how can we set up a permanent database for MISO so that MISO staff can, MISO or their participants can use it as a resource going forward. So we want to work with you. Please email me if you're interested in learning more. Next slide, please. So here, I think, are some of the informed questions that commissioners can ask about forecasting. So I apologize because this is normally a 1-hour talk, so I've condensed it to 10 minutes. But just thinking about, for people that are developing forecasts, what are the primary factors that drive the forecast of adoption? Does it consider economics only? Are there other factors that are influencing the forecast outcome? How do these forecasts tend to account for an observed phenomena that new technologies follow an S-shaped curve of adoption, that initial adoption is quite limited, and then there's an acceleration period followed by sort of an asymptotic saturation? Thinking about, are there other sources that you could compare forecasts to? There are, at this point, several third parties that develop forecasts, either publicly or through licensed reports. And then thinking about, to what degree is the forecast driven by top-down methodology versus bottoms-up, and how do you connect these forecasts to either at the consumer level or at the feeder level? Next slide, please. So that's it for me. Thank you for the whirlwind opportunity, and here are some resources to get you started if you have some more questions about the state of the literature. Thank you so much.
Thanks, Ben. We'll next hear from Patrick Dalton from ICF talking about hosting capacity and interconnection. Thanks, Patrick.
Thank you, Lisa, and thanks, Ben, for that presentation. That was great. Again, my name is Patrick Dalton. I'm with ICF. Happy to be back here to talk about hosting capacity and interconnection. So kind of starting just with the takeaways right off the bat. Similar to what Paul was saying about grid mod, hosting capacity objectives are a very important starting point to ensure that the result is actually usable in a way that stakeholders are expecting it to be used to achieve those benefits. So we'll talk a little bit about objectives. We'll talk about a few of the different fundamental methodologies that are available. There's really 3 main methodologies that are in use across the country, and they have some trade-offs that we'll look at. And then finally, want to look at some of the different methods across the country in terms of granularity and system information that's presented, because it does differ quite dramatically from region to region. Next slide, please. So starting with just the basic, what is hosting capacity? It's essentially the amount of DER that can be accommodated on a circuit with existing conditions. So the existing equipment, the existing load, and the existing generation that's already been interconnected, while maintaining safety, reliability, power quality, sort of the core objectives to utilities. It's typically presented in a map form to the right, but the underlying data is also useful for some of the use cases. Next slide, please. And just briefly, where does hosting capacity fit within integrated distribution planning? It can be used to inform interconnection studies. That's one of the use cases that we'll look at, but it can also be used for sort of longer term distribution planning, looking at where upgrades might be needed based on DER adoption, or informing locational value, which Debbie is going to talk about a little later. Next slide, please. And so looking at 3 of the most common use cases and thinking about the importance of really spelling out the objectives and the use case prior to embarking on a hosting capacity effort. The first use case, the most common one today, is informational maps for developers, so outward facing maps from the utilities that can help guide DER to locations that can accommodate the resources without upgrades. The next is automated screening. So the hosting capacity results could either be used through a manual process for engineers to streamline the screening process for interconnection, but also it could be used in, in an automated fashion to really streamline interconnection to minimize the manual labor that's really needed to review interconnection applications. And then finally, as a distribution planning tool, and this is probably the least developed use case, informing locational value is something that's being done in some jurisdictions, but the broader tie-in with distribution planning and hosting capacity is still really being worked out. Next slide, please. So looking at how some of the different jurisdictions that have adopted hosting capacity, and this is a non-exhaustive list, but mapping some of these use cases, it's pretty apparent that the outward-facing maps for developers is really the primary use case. And other jurisdictions have started to look at the technical screening use case and the distribution planning tool use case, but those are earlier in the progression. Next slide, please. And now looking at a specific example in New York of how stakeholders are currently applying hosting capacity maps, I think it's somewhat intuitive that the highest value for stakeholders or the highest use case is just simply what remaining hosting capacity is on the system. But beyond that, hosting capacity maps can start to provide information about whether there might be upgrades, kind of more costly upgrades. 3V0 is an example here. It's a specific substation protection type of technology that can be quite costly. And so hosting capacity maps can also furnish that type of information if an upgrade has already been performed at a substation, or if a developer might face that upgrade with their project. Next slide, please. So now kind of zooming in on this interconnection use case and thinking of hosting capacity as a tool to streamline interconnections, there's really kind of two places that it can tie in. One is in this pre-application phase of providing developers with that information up front that we were talking about. It can supplement or even supplant the process of pre-application data where a developer approaches a utility with a specific location and asks for relevant interconnection information for that location. But it can also be introduced later on in the process during what's marked the supplemental review here, which is an engineering analysis to look at voltage thermal protection limits. We're going to do a very fast overview of what those limits are in a few slides here. Next slide, please. I mentioned that there are three main types of hosting capacity analysis. They go by different names, but streamlined, iterative, and stochastic is one framing of these. The streamlined is a method that's EPRI drive tool is probably the most prominent example of this method, and it uses simplified algorithms, kind of simplified calculations, and not a full power flow methodology. And so it's not quite as accurate as the iterative method, which actually is performing the type of full-blown power flow study for every location on the system, very similar to a study a planner would perform during an actual interconnection study process. It's iterative is more computationally intensive, so it can take more time to run the scenarios, which becomes more of an issue with very frequent updates over an entire system is where you may start to reach some of those limitations. And then stochastic is a third method that sort of randomly places DER at different locations on the system in order to come up with a range of different hosting capacity values. And this has been incorporated in some commercial software and by some utilities. But I tend to think that streamlined and iterative are bubbling to the top. But as we'll see here on the next slide, There's, oh, excuse me, this isn't the next slide. It's actually a little bit later, but anyways, next slide.
Patrick, why don't we break in here for the poll?
Okay, yeah, that sounds great. Okay, so the question is about how your state is using hosting capacity analysis currently. So is it not currently available yet, or are there maps, or are there some of these more advanced use cases? All right, thank you for your responses. So the majority of respondents said that hosting capacity is not currently available in your state. So I think that I'll maybe reemphasize the point again about how important objectives are prior to really embarking on a hosting capacity analysis and really clarifying what those are. So I guess hopping back into the presentation here, I just want to flag how data integrity is really a persistent challenge for hosting capacity. This is similar to like a ADMS adoption or other systems that really rely on the system data being available and accurate. But as we think about the more advanced use cases of actually approving interconnection applications based on an automated method that maybe doesn't have somebody looking over the data in the analysis, this data integrity issue becomes even more prominent. And there is an example of Southern California Edison actually developing an automated process for improving their accuracy and accounting for system changes, because the distribution system is very dynamic and changes all the time based on storms or upgrades or a number of other factors. Next slide, please. So now we're going to do just a very quick overview, next slide, please, of the different types of technical criteria that hosting capacity is looking at. So we're going to quick fly over each of these bullet points, covering voltage, protection, thermal, and reliability considerations. Next slide, please. So this chart may look familiar if you happen to sit on my presentation from yesterday, but reverse power flow from DER can create high voltage, and there are set limits that equipment can tolerate. And so an important evaluation during hosting capacity is just what is the steady state voltage going to be after DER. Next slide, please. Another voltage related issue is looking for the voltage change from a DER unit being on to a DER unit being off. It's called voltage fluctuation sometimes, and there are a couple components, but the one that is most relevant here is a rapid voltage change limit, that if there's an abrupt change in the output, and there are a number of factors that can cause that, not so much like cloud cover, something that's an even faster event, there can be a step change in voltage, and that can cause equipment problems. Next slide, please. Thinking of capacity constraints, thermal limits are really driving capacity constraints, the amount of power that can be pushed across a conductor. And where a limit may be reached in hosting capacity is where the level of reverse power flow starts to encroach upon the equipment rating limits. So this is another key criteria for hosting capacity. Next slide, please. Kind of on the unintentional islanding slide, and the question came up of, are inverters capable of forming islands or other generation on the last presentation. When inverters are in grid-connected mode, or any DER for that matter, it's important from a safety and power quality perspective to assure that that DER won't energize a part of the line that's disconnected from the system unless it's intentionally designed to do so in like a community microgrid or multi-user microgrid approach. So flagging the potential for load and generation to be matched where an island could occur is another threshold that's commonly applied. Next slide, please. Kind of continuing down the protection side of things. I might be having a lag on my side. Thank you. There's this concept of relays being desensitized. So the inability of the utilities relay to detect an issue on the system is kind of this desensitization issue. And when DER feeds a fault, so if there's a tree that falls on the line and both the utility system and the DER are feeding that fault, that can lead to this desensitization phenomena. And it's really important for a safety and reliability, from safety and reliability perspectives, that utility relays can detect faults on the system and quickly isolate the problem. So if DER is added and it prevents that ability, that's an issue, and that's something that hosting capacity is screening for. Next slide, please. On the operational side, some hosting capacity methods, and this is maybe in the minority currently, but some are looking at this operational flexibility. So if the system needs to be switched around, and we looked at an example on my presentation yesterday where there's an issue with one of the substations and now DER is served from a different feeder or a different substation. If we don't plan to be able to accommodate that DER in the alternative configuration, then it may be forced to go offline because it's causing some sort of voltage or thermal issue. So including a margin for operational flexibility is a feature of some hosting capacity analyses. Next slide, please. And then finally, in terms of the kind of technical impacts, there's the potential for constant changes of DER output based on cloud cover for solar or changes for wind causing fluctuations in output. And if there's equipment nearby that's intended to respond to changes in voltages, these output fluctuations can cause this equipment to operate very frequently. And that's what we're looking at on the right-hand side is this study that was performed by NREL looking at how many times a piece of equipment would need to change taps. You know, this is voltage regulation equipment mechanically actually switches contacts, mechanical, metal contacts. And so there can be wear and tear that we need to watch out for. And so that's a common threshold for hosting capacity as well. Next slide, please. Next again. So we're going to very briefly cover some of the features that hosting capacity maps or analyses may include. And we can just go right to the next slide, a summary of some of the features and the methods. I'll include this mostly as reference to look back on, but I do want to flag on the left-hand side the analysis methods, the 3 different methods that we discussed. And there's more in the streamlined and iterative columns, a few in the stochastic, and then in terms of some of the features, we'll look at these in detail, but it does vary from map to map or analysis to analysis. Next slide, please. There's been a trend towards including pop-up information on hosting capacity maps. So instead of just having a color-coded map that shows the potential hosting capacity, actually including some of that pre-application data that I mentioned as well in a pop-up window. Next slide, please. We'll actually skip this one as well, but if you want to look back in terms of what pop-up information is useful, there's a slide on that. Another feature that's becoming increasingly common is specifically calling out PV hosting capacity versus other types of DER. And what this is doing is really just taking into account when PV is producing and the load at that time. And with PV being a very prominent type of DER, this can be useful. Next slide, please. EVs and load more generally is a feature that's starting to pop up more and more in hosting capacity maps across the country. So this is an example of a national grid map, but Pacific Gas and Electric also has load hosting capacity. A number of others do as well. So as we're thinking about beneficial electrification, this may be an important feature to ask for as well. Next slide, please. Wanted to briefly show that there is a range of granularity in different hosting capacity maps, kind of starting on the left-hand side, blocks that show kind of regionally what the hosting capacity might be. In the middle is sort of more of a heat map where the lines are blurred, and then all the way to the right-hand side is sort of actually showing the feeder lines. And there can be privacy concerns potentially with different levels, but it's good to know what kind of granularity you're aiming for as well when embarking on this. Next slide, please. I'll just very briefly mention that locational value is a feature in very few maps currently, but could become increasingly important. And Debbie's going to talk more about how locational value can be used. Next slide, please. And then sort of an advanced feature as well is actually allowing users to download load curves or even just all of the hosting capacity results for a location. And this is an example from Southern California, Edison. Next slide, please. And very briefly, just want to talk about some of the limitations of hosting capacity data. We talked about that. As you get further up in the system, kind of substation transmission level constraints aren't always accounted for. Downtown networks are a very specific design. It can be challenging to account for those in hosting capacity. At the other side of the spectrum from substation transformers, as you get very close to the customer, there can be data challenges with that information as well, and so that's not always available. And then employing smart inverter functions and settings as mitigations to understand, if smart inverters are used, what the hosting capacity could be is another challenge that's being addressed. Next slide, please. I think in the interest of time, I won't read these questions to you, but they were sort of sprinkled throughout the presentation. So a couple things to think about as you're considering hosting capacity. And the next slide is resources for more information. And thank you for the time. I know that was a bit of a quick flyover, but I appreciate the opportunity to speak with you today, and I will pass it over to Debbie now.
Thanks, Patrick. Can you guys hear me okay?
Yes, you sound good.
Yes.
Great, thank you. So I apologize in advance. I had some emergency dental work done this morning, and I'm going to try really hard not to bite my tongue while I'm talking. But I'm going to talk about locational net benefits, DER compensation, DER implementation. If you go to the next slide, as you can imagine, there is no one size fits all answer. That's because DER are so many different things, right? They can be generators, storage, demand response, energy efficiency. And also there is a difference between the value the DERs provide and the avoided cost to the utility and the compensation that they earn. And then finally, compensation depends on how it's implemented. Are you going to issue an RFP and choose the least cost, or are you setting a price and looking for organic uptake, or are you trying to incentivize something? And then finally, because DERs can provide a specific service at a specific time in a specific location, the evaluation can get really granular, and this can be cumbersome. It can also raise equity issues. You know, should I be treated differently from my neighbor because of where we are on the meter? It can also get at the heart of really unlocking the value of DERs, though. Now, there's different ways to pay for DERs. Net metering is most common, but you could also set a tariff for what you'll pay. And that could be based on the value of DER, or you could have a feed-in tariff based on avoided cost. Because net generation or net consumption is often a basis for compensation, and because some DERs are load modifiers, rate design becomes really important. And then finally, non-wires alternatives, they're different. These are alternatives to traditional T&D upgrades. And utilities issue RFPs for non-wire alternatives, and then they select the least cost solution that's going to meet their needs. And compensation there is based on the offers that are received. But in order to determine, you know, which projects they should go out to bid for, the utility uses locational net benefits analysis, and that's what Patrick just showed on those maps. And the locational net benefit analysis is essentially the avoided cost of the traditional utility solution, and they use that to help them prioritize projects. So I'm going to talk about procurement, pricing, and programs, and it's going to be a little bit fast here. So let's go to the next slide.
And Debbie, we're going to queue up a poll here.
Oh, okay, sure. So we just wanted to try and get a sense of what folks were doing in terms of deploying DERs in their regions. And everything. That's great. Okay. So we're going to start talking about non-wires alternatives. So these are hot right now. Wood Mackenzie recently issued a report showing about 850 megawatts of non-wires alternatives that have been identified or implemented in the US. But implementation has been slow, and non-wires alternatives are not yet, you know, a really big market share for DER providers. Projects are only moving forward about 40% of the time. It used to be that energy efficiency was a big non-wire alternative. Now it's battery storage. Tends to be front of the meter. Ben just talked about front of the meter, so not netted out from generation behind the meter, but rather its own metered resource. FERC Order 841, which allows storage as small as 100 kilowatts to access wholesale markets, is probably going to encourage more storage solutions in non-wires alternatives because you'll get more value stacking. In addition, costs are dropping. So why aren't more projects moving forward? Some of the big reasons given is that they're more expensive than traditional upgrades, or they're less reliable than traditional upgrades. If you go to the next slide, we're seeing non-wires alternatives mostly being identified through the big processes, through the New York REV process, the California DRP process. In some cases, like in Vermont, the utility is required to prepare a long-range transmission plan updated every 3 years, get enough time to identify and implement cost-effective non-wire alternatives. Obviously, a utility that's under cost of service regulation is going to be incentivized to spend more money on infrastructure. So there's also new innovations coming out, like Central Hudson Gas and Electric. They split the savings in non-wire alternatives so that 70% of the savings accrue to customers and 30% of the utility. And that helps incentivize the utility to actually do non-wires alternatives as opposed to the traditional solution. You go to the next slide, I'm going to dive in deeply to California and their distribution investment deferral framework, because it's a really nice framework for how one might think about setting up a process. So first, the IOUs establish their historical peak demand, and they forecast their load and their DERs. They do all the stuff that Ben talked about. And they disaggregate all this down to each substation feeder. Do a study for each of these feeders to ensure that the system can operate under normal conditions, under abnormal conditions. And if they have a problem, they identify, where's the need, what kind of need is it, is it a capacity problem, a voltage problem, when does it kick in, what hours does it happen? And then they develop their own utility-owned traditional projects to fix these needs. Now you start with the cheapest things, like maximizing use of existing equipment or modifying the circuitry. And then you build up to more expensive things like a new distribution circuit, or really expensive things like a new substation. And then they screen these projects, and they look at things like timing. Is there enough time to do a solicitation? That can take 3 years to go through that whole process. Can DERs help with this problem? And what you can see here on the right, the top shows 262 grid needs that SoCal Edison identified in their process that they issued in 2020. And then the middle right shows that when they screened that for timing technical screens, they got down to 14. And then at the bottom, this shows their prioritization of these 14 projects. So they use 3 metrics: cost effectiveness, where they use this locational net benefit calculation, which again is the avoided cost to the utility of the traditional solution. And so some expensive traditional solution, that would be a really cost-effective potential project, and that would be rated green on this metric. And you can see that in the first column here. And then forecast certainty is the second metric. So do they really need it? Do they know they need it? Do they have SCADA measurements to justify this? That would give them green in this second column. And then market assessment. Does the current DER market fit the problem? Is it a 4-hour need, or is it a 12-hour need? Is it something that's predictable or unpredictable? If it's 4 hours and it's predictable, that would get you a green on the far right column here. And you can see they rated their 14 projects. The top 2 tiers that are all yellow and green for these metrics are the ones that SoCal Edison decided to go forward with in this example. So if you go to the next slide just shows that there's a number of different behind the meter or in front of the meter aggregations and technologies that they're interested in, and also that they're thinking ahead to wildfire mitigation and behind the meter solutions that can provide resiliency with other things going on in California right now. And if you go to the next slide, this shows an example the Eisenhower project. So the blue is the crosslay circuit coming out of the Eisenhower substation. And I realize it's hard to see, but the bottom right table shows in red that starting in 2022, they're going to start to be overloaded on that circuit. They're going to run out of capacity, and the hours of the need are 5 o'clock, 6 o'clock, 7 o'clock, and they're going to need a maximum of 2.5 megawatts and 4.4 megawatt hours for that particular need. So this gives you an example of what this looks like. You go to the next slide. I wanted to explain a little bit of this process that they just went through. So SoCal Edison filed their grid needs assessment and their distribution deferral opportunities with those 6 projects that were proposed for doing an RFP. They filed that in August 2019. CPUC approved that in December, and SoCal Edison launched the RFP in January. So, that took a little bit of time right there on its own. And at the end of their peak season, they run through another distribution planning cycle, and they found as they ran through this next cycle of planning that things had changed a lot. So the 6 projects that are shown on the 2 right tables here changed a lot. And you can see from the 2019 column and the 2020 column, 2 of the projects are no longer even needed. Pachanga and Alessandro, the 2 in the middle. And the other 4 had drastic changes. And in particular, that one that I just showed you, Eisenhower, on the bottom left of this table, you can see that the need went from 2.5 megawatts to 16.2 megawatts. Now, the traditional upgrade cost is still the same, but what the DER providers need to do on their side in terms of what kinds of capacity installation they need to put together, it needs to be much bigger now. And unfortunately, because this was so late in the game that this happened, the bidders were given a week to revise their bids. And so this was a little bit of a unhappy situation for folks. And it's just an example of some of the challenges that can occur in the procurement process. And so obviously there's things that maybe we need to do to try to align some of the planning cycles better with some of the bidding cycles. It also just points to the fact that these things are moving targets and there are a lot of changes going on in the system. Okay, so now if we go to the next 2 slides, I want to talk quickly about pricing. Various ways to think about how to set tariffs. For example, some places like Hawaiian Electric used to have feed-in tariffs for different technologies because they wanted to encourage uptake of different technologies. New York is working on value of DER. Austin has long had a value of solar tariff. What do these calculations look like? So here's an example on the right of a value of rooftop solar calculation. And it's showing a stacked value for different solar penetrations for municipal utility. And for each of these, example, distribution losses, you could run a distribution power flow and calculate losses on sample feeders. For energy and transmission losses, you could run production cost modeling and transmission load flow analysis to calculate those. You could run a loss of load probability analysis to calculate avoided capacity. And then there's a lot of other additional attributes, fuel price risk, avoided RECs, emissions. So there's a lot of potential weeds that you can get into and a lot of opportunities for conflict in these kinds of calculations as well. If you go to the next slide, one of the things I wanted to point out in this particular example is that this particular utility, in addition to evaluating a value of solar tariff, they wanted to look at different rate designs because they wanted to close that gap between the cost of servicing their PV customers and the revenue that they received from those customers. One of the things we looked at for them was time of use rates and how they acted like storage on the system and provided a lot of savings just on their own. And this is just looking at time of use rates and how much value they would bring to the system in terms of capacity and energy compared to what this low scenario here is 13 megawatts of PV. So it provided, a similar kind of value to the system just in setting the right prices to begin with. And if you go to the next slide, as you all know, DERs are much more than just rooftop solar, right? There's lots of DER technologies that can shave load, shimmy, shift load, and this is really the low-hanging fruit. But in order to get at this power, you've got to have strong price signals and enabling technology. And that's what this graphic is showing. This is the summary of hundreds of experiments done in dynamic pricing, looking at the impact of having a high peak to off-peak price ratio and enabling technology, which is shown in the lighter blue dots. So providing both of these things can get at a much stronger impact. And then if you go to the next slide, I won't dwell on this, but ERCOT is a really good example of how very strong pricing, how demand response, and how their 4CP program, which is basically a coincident peak cost allocation process, really helped them to meet peak load with a really tight, less than 9% capacity reserve margin. So if you skip over 2 slides, we're going to talk quickly about programs. So one of the programs I wanted to mention was Holy Cross Energy. This is a really small distribution co-op. They don't have a lot of staff or a lot of resources, and they've really tailored what they do for the biggest bang for the buck. So they focus on electric vehicle programs where they essentially trade you a level 2 charger for the opportunity to control your electric vehicle charging. They also have a peak time rebate program where they pay you up to $1 per kilowatt hour for critical peak periods. And they're working on a distributed battery program currently. And I'll also say for their peak time rebate program, there's no penalty for non-performance. There's only an upside for customers. And I just say this because it's in contrast to what we see in demand response programs where, you'll tell customers you're going to call on them 100 hours in a year, you get to the 20th hour of the year and they start getting upset. Or in contrast to a program where they may be financially penalized for non-compliance. This is a really nice, everyone likes this program. Okay, now if you switch to the next slide, I wanted to talk also about a large utility, so Arizona Public Service, who is a leader in pricing and programs. So they realize DERs, electrification, if we don't control this can exacerbate grid issues. But if we can control these, either directly or through pricing, this can fix or alleviate grid issues. So what APS did was they partnered with Energy Hub. Energy Hub provides the DERMS, so that management system for all the DERs, and they're customer facing, they do the communications and control. And APS thought about a lot, they have a bunch of different programs. I want to focus in on just the first 2 here. They thought about, should it be bring your own device? How should we replace out water heaters? It turned out they had a couple specific feeders with issues they wanted to address. And so they targeted 2 programs to those specific feeders. And instead of waiting for organic turnover of the appliance, they said, we're just going to give you essentially a free water heater in exchange for control of it. And with storage, the utility gives the customer a $500 credit. They own, they maintain, they control the storage. But if there's an outage on that system, the customer can use that battery for backup. If you go to the next slide, then APS sort of brings all this together, and it's really critical to think about the situation that your utility is in. APS is in a situation where they're right next to California, right next to high levels of solar. They got high levels of solar themselves. 1 out of 4 days last year, they could buy negative priced energy in the regional market. They're looking at their existing programs, eliminating those programs that are exacerbating their duck curve, and instead focusing more on programs that are helping them with peak and flattening the load shapes. And I just wanted to show what they're doing there with that camel-shaped curve. They basically have really strong time of use rates. So there's a peak ratio of 7 to 1. Time of use ends, the off-peak ends at 3 p.m. And they wait until after the peak rates hit a little bit. And then they put in their 2-hour demand response to help kind of flatten that out a little bit more. And that helps them kind of orchestrate their load profile. It's a little crude, but it's still very effective. And the next slide is basically just some questions that you might want to ask your states about procurement. And the slide after that is just resources for more information. Thank you.